Hey guys, my name is Jason Schuster. I'm a doctor of physical therapy. I own Integrated Art Spine and Body Solutions. It's a continuing education company teaching other doctors how to do a couple things. If you have this medical understanding, you can take it upon yourself to help yourself if you're not a medical practitioner. And if you are a medical practitioner, you can utilize this information to both help yourself and help the health of your patients. So this is absolutely vital information to have. It is impossible to be healthy, optimally healthy, without understanding this stuff. And the reason that eating well and the reason that exercising and the reason that taking supplements and stuff in the proper way helps is because it affects your epigenome in positive ways. And then things that you do like eating processed food and not exercising harm you because it's affecting your epigenome in a negative way. So the epigenome, as far as we understand right now at least, is you can think about it as like the most elevated level or the most base level, however you want to think about it. But all humans more or less have the same genes. It's how that information gets read and expressed and translated is what determines people's phenotype. So what makes you tall is not the fact that you simply have tall genes, right? Everybody's got those genes. It's that those genes in a tall person are turned on or expressed more or expressed in a different combination with other genes than short people are, right? It's really, really interesting. And this is a huge misconception in medicine because hardly anybody thinks this way about genes. Most medical practitioners and most people in the United States think that whatever your DNA says is what you're going to turn out to be, and that's just not true. So there's a bunch of genes in the body that are considered longevity genes. So there's some really good research on a lot of this stuff. David Sinclair at Harvard is one of the best ones, you guys. He's got a good short 8-episode podcast and he does tons of research. He's really, really up to date on this stuff. And there's a ton of researchers all over the world that are looking at these genes and how we can turn them on/off depending on what we want to do and what they do to the human body. So there's a handful of genes that have really been heavily or more heavily studied than other genes and other proteins that they make thus far in the literature. So 4 of the most commonly discussed vitality genes or longevity genes, genes that improve your health span and your lifespan, are sirtuin genes and proteins, right? The mTOR genes and proteins, AMPK genes and proteins, and then the telomerase and genes and proteins that make telomerase that help heal and repair and lengthen telomeres, right? So we're going to go through those 4 things and we're going to talk about what they do more or less, why they're important, and why nutrition and supplementation and eating well and exercising and doing treatments like dry needling and joint manipulation and just generally taking care of yourself in a thoughtful, objective manner, why that turns on these genes in a way that makes us healthier and live longer, right? So these are very, very powerful genes that very, very few people have heard about and almost 0 people get taught about in medical school. These are the 12 most commonly referred to signs of chronic aging or hallmarks of chronic aging, and that can be extended to hallmarks of chronic sympathetic hyperactivity, right? The most common denominator between all impairments in adults is chronic sympathetic hyperactivity. Now, the reason that chronic sympathetic hyperactivity is there may differ relatively largely among groups of people, but the fact that it's there remains the same. So it could be from eating too much processed food, again, not exercising, mental stress, physical stress, a whole bunch of stuff. But the 12 hallmarks of aging, you guys, and number 1 is the most consequential in my opinion, is genomic instability. So that would be a dysregulation of your epigenome, which is dysregulating the way that the actual DNA is getting read. So as far as we understand, only 0.1% of DNA is different among humans, and it's the way that the DNA is expressed or what alleles of each gene the people have and which ones are dominant, which ones are recessive. There's a huge amount of possibility after the fact of, yes, everybody's got these genes, but it depends if they're turned on or not. Again, only a very tiny percentage of people actually have a different genetic makeup, like people with trisomy 21 or Down syndrome, where they have a triplication of the 21st chromosome, right? That's a major change that is extremely rare in human beings, thank goodness, and it's amazing that it is, right? I'm always stunned that more things like that don't happen. So, number one, genomic instability. Number two, telomere attrition, or shortening or dysfunction of the telomeres. We're going to get to that in a second. Epigenetic alterations we mentioned with the genomic instability, loss of proteostasis, or the ability to make proteins, which comes from a loss of mitochondrial energy and a energy deficiency in ATP, which dysregulates the way that our body can read our DNA and how it reads our DNA, right? Mitochondrial dysfunction, again, mitochondria are the base source of energy in our body. If mitochondria dysfunction, everything else is going to dysfunction because we're not going to have enough ATPs to properly function. Remember that one ATP more or less will produce one mitochondria more or less will produce 36 ATPs per molecule of glucose processed with oxygen. Without oxygen, one mitochondria only produces 2 ATPs per molecule of glucose processed. So that's an 18-fold difference just in the amount of oxygen or no oxygen. And that also gets affected by the amount of minerals and elements that we have. If we have deficiencies in vitamins like vitamin D, vitamin E, vitamin C, vitamin A, zinc, all those affect the way that our body can produce ATPs and energy. Cellular senescence. Number 6, number 7, altered intracellular communication. Number 8, that's what happens with chronic sympathetic autonomic nervous system hyperactivity, mineral deficiency, a whole bunch of stuff. All of these things are negatively affected by not having the proper vitamins and minerals in your body, you guys. And we go over this in detail, in depth, in the 2 parts, part 1 and part 2 of the nutrition supplementation class. We go over vitamin and mineral deficiencies. We go over what supplements I take and what the amounts that I take. And we go over why taking those things helps with all of these 12 factors, right? Stem cell exhaustion. So our cells hit the Hayflick limit, right? So the Hayflick limit more or less is just the pre-programmed amount of times that a cell can divide before it dies, right? Dysregulated nutrient sensing. Again, we talk about that in depth in the nutrition and supplementation classes and the peptide classes. Disabled macroautophagy, or basically the ability of our cells to clean themselves up or to clean the garbage out of themselves. If the cells don't have the energy to gobble up the misfolded proteins and the excessive pro-inflammatory proteins and whatever else is in there that they need to clean up, if they don't have enough energy, they can't clean it up. So dysregulated nutrient sensing, disabled macroautophagy, chronic inflammation, that's one that we talk about through all of these online classes, you guys. Chronic inflammation is one of the hallmarks of aging. It's one of the simplest hallmarks of aging to address. And by addressing inflammation, you're also addressing genomic instability, telomere attrition. So if you address one of these things in some way, shape, or form, you're most likely going to be helping the other ones. And if you can address these things specifically, they all work in synergy with each other. So as one gets better and more homeostatic, the other will. It's just the way the body works. Everything is connected to itself, right? So like I mentioned, I look at genomic instability as the number one driving factor of this, because if the epigenome is not functional and the autonomic nervous system is not in homeostasis, our DNA cannot be read properly, and the different genes won't be expressed in proper ratios to each other, right? So this is why it's so complicated. It's not just that, oh, you have this gene that's turned on, it's how much is that gene turned on? In what relation to other genes is it turned on? How much is it turned on or off compared to those? What are the other genes that are turned on?